Hi, this is the third section for lecture 6, random variables, and this section we are going to learn about expected value. So, what is expected value? We can kind of guess from the definition itself, right? It's the value that we expect to see or expect to get, and with the addition keyword that in the long run. If you roll a dice, there are 6 faces, you are not going to know what is going to come up. But if you roll dice again and again and again, right, then you expect, right, what would you expect in the run? In this case, it's about the average. Right? You are going to get 1, 2, 3, 4, 5, 6, maybe 5, 4, 1, 1, 2, 5, and so on. The values are going to be random. But we can kind of see the pattern, see the average in the long run. And so the motivation here is this is where it's kind of the middle ground for statistics and probability. In statistics, we use the word mean or average. And it is in stat. And that is when you take all the values, take all the samples and find the average. And add the values together and divide by the number of data points. But in probability, in this part, the math part, right, we only have the theory. Right? We know the probability of some value to come up. And of course, we can generate. Like if you put the probability for each event into some software, some program, we can generate the sequence of values. If you set the program to generate number from 1 to 5, and each of the values is equally likely, then the program will just, give you an output of 1, 5, 5, 3, 4, 2, 2, 1, and so on. But then, if you want to find the average, right, on average in the long run, what would be the middle point of all the values that you give it? And this is what we define as the expected value. Right, so let's go through each point. Yeah, this is where we use probability to get the statistics when we want. Then the definition that we define at the beginning of this class, this lecture, it only tells you the probability of a single event, just one event. You can adjust the number to be anyone you want, but it's just one single event. And then what we would want to ask, what happens if you want to know what would happen in the long term, if you take into account of all the events altogether, and what can you say about the whole experiment? Right on. Or if you want to know what happens if you repeat it in the long term, that means pretty much the same thing as if you repeat the experiment again and again. Gazillions, is the word? I don't know. Gazillions number of times. What would be the average? And for example, if you have 2 bags, in the first bag you have 1 green ball and 1 pink ball. In the second bag you have 3 green balls and 1 pink ball. And you can kind of see that the second bag, this one is kind of like skewed because there were too many green balls than the pink ball. And then if you pull a ball and take a ball out and take a note what color it is, put it back and repeat. Maybe that's gonna get another green, and then that's back to pink, and then green again, and pink, and so on. And that will be the sequence of experiment. For each experiment, you take a single ball out, take note of what color it is, and repeat that. You're gonna get a sequence of colors. And likely, similarly, for the second bag, you can repeat the same thing, but suppose that you don't know the content of the ball. Like you cannot see what are inside of these 2 bags, and then you just pull those out at random and take some notes. And you're gonna see again another sequence of green and pink. In this case, let's say that there are like 10. You repeat that 10 times for each experiment. Yeah, but that's just 10, right? 10 is small in statistics and in math sense. To be large enough, it has to be large enough. Maybe 100, maybe 1,000, maybe even 1,000,000. It depends on how you define the word large. But in that sense, maybe they look similar. in the short run. But in the long run, you can kind of have a intuitive sense that in the second bag, right, you will see a lot more green balls than the pink balls, just because they are more. It is more likely to get the green balls, one of the green balls from the second bag. And so in the long run, you would expect to see more green balls, and that's what your expectation. And now we are going to define that expectation, that tendency, in terms of math that we can compute. And that's the definition. So maybe you shouldn't look at that yet. Let's think about the green ball for a moment. I mean the back with green and pink balls for a moment. And let's suppose that let's say you count the green ball as 1 is the one that you want, and for the pink ball is the one that you don't want for whatever reason. And so it's going to be a sequence of 1 and 0, which we will denote as both the color green and the number. And then let's say it's just 10, right? You can what? This is just a sample. You repeat the experiment 10 times, you get this sequence. And from these small samples, you can ask what is the mean or the average of all these numbers. In this case, suppose there are 10, and there are 10 balls, and you have 6 green balls. You would say, okay, so I got 6 balls of value 1 plus 4 balls of value 0. Of course, you can write the sequence as 1 plus 1 plus 0 plus 1 plus 1 plus 0. That's like a long way to demonstrate this sequence. We can abbreviate, just count how many green balls are there and multiply that by the value. That's going to be easier. And actually, we have the word for this one. They are what we call the frequency. How frequent is each of the 2 balls came up. So that's the frequency times the value. Okay, again, frequency times value divided by the total frequencies, the total number of balls. So in this case, in the first case, just the first line, the average is 6 plus 0 over 10, which is 0.6. Nice rounding decimal. Oh, sorry, it's out of screen a little bit. So it's 0.6. Okay, so that's the average from the sample. We can repeat the same thing here. How many green balls are there? 1, 2, 3, 4, 5, 6, 7, 8. No, sorry, 7. See, I'm not good at counting. 7 green balls plus what? 3 0 balls. We still write it as 0, so you can see that we do take into account other balls. Right, so again, the 7 plus 0 over 10 is 0.7. And here, this is what we call the mean or the average of the values inside these 2 bags. And these are the average when we take into account of the values and the frequency. And you can kind of see that we can, instead of looking at it as as summing the total up and then divide by the frequency, let's just say for example for the first one, you can think of it as if you distribute the denominator across the sum, it's going to be 6 over 10 times 1 plus 4 over 10 times 0. So another way to look at this formula is we multiply the value of each ball, right, by the density. And we use a slightly different word. Like previously, we used the word frequency because we simply count the whole number, how many times we see the number. But here we use the word density because we count the number of times and divide by the total number of observations or number of experiments. We repeat. And so in another way, we can express the same formula for the mean as this formula. And so the density, or how often we see the 6 across all experiments, and times the value. Oh, sorry. And this is another way to look at the formula. right? And this is exactly what we are doing here for the expected value or expectation. And so if you look, and now you can look at the formula now, right? So this formula, you can see there are two parts, actually three parts. Right, so we have this symbol which I will go over in a moment, and we have these two parts. Okay, so first this symbol, like this strangely looking E, like this is the summation symbol. It means we add all the terms together. But since sometimes they add too many terms to write, and so you can write as A plus B plus C plus D and so on. And that's really the long expression. So you can abbreviate as summing of some terms. You repeat the term over and over. In this case, we sum all of what? We take a summation for each of the x in S. And what is S then? S is the sample space or each outcome. X is an outcome. And so first you look at how many outcomes are there. If you roll a dice, there are 6 outcomes. If you flip a coin, there are 2 outcomes. If you take a random number from 0 to 9, there are 10 outcomes, for example. And you're gonna take a sum for each of the outcome. You're gonna do what? You're gonna take the product of the value. That value is part of the sample space. It's the value times what? Times the probability of that event. Value times probability. And again, if you take a look at the right, that is exactly what we did for the average, for the mean. Just write them slightly different way. Let's just take the sum of all possible outcomes. And for each outcome, you take the product of the value and the probability. And that's going to give you what? The average. The average here, or the mean. But in this case, it is a mean from the theory, from the formula that we define, not from sampling. And that we have two different notations. It's a mu. And this mu is the usual average, which we gonna not use too much because it's gonna be confusing. And we will use this E of x, which will be expectation of the x. What it is? You remember what x is? It is the random variable. We have to define x as a number of something, and that's gonna like remember all the probability for each outcome. And then when you take the average, here we use the word expected value. And it is from this formula. And again, that describes. Should I move to the left? Yeah. That describes the long-term average. If you repeat that enough number of times, you're gonna get to this average, without having to start doing the experiment at all. If you have all these numbers, you can compute the expected value, and you can kind of guess in advance that if we actually use these numbers in the real world, then the average should be close to what we have already computed beforehand. Alright, for example, let's take a look at this one. So find the expected value of a single die roll. So you roll a single die, then that's the question. In other words, find E of x, where x is the value of a die roll. And so now we have kind of two different ways to define this kind of experiment. First, we use let's say what the normal people use. Right, we can replace that by the average. Sometimes you will see the word kind of like theoretically. I don't even know how to write that. Okay, so the average in theory. But the better word is expected value, right, of a single die roll. And that's what you will be interested in. And in math notation, we are looking for E of x when x is the value of a die roll. Right? So let's do it. So do you remember what the formula of f x is? Right, it's summation of x of across all the samples, all the outcomes. You can read it as for each outcome. You take the value and multiply that value by the p of x. Oh, it should be capital. Right, that's the formula. So before we proceed with the formula, instead let's use the intuitive way of how you would compute the average. Right, so how many values are there? There are 6. 1, 2, 3, 4, 5, or 6. There are 6 different values, possible values. Let's use loaded dice or something red. And then for each value, how often do you expect each outcome to come up? You would expect one to come up 1/6 of the time. You know, in other words, if you roll the die 6 times, you would kind of expect to see number 1 once. That's what it means by the product here. And then for 2, similarly, let me write it this way. You would, if you roll 6 times, one of the possible outcomes is to get each of these number exactly once, and then you kind of divide it by the number of times you roll 6 times, and then you kind of. This is just the idea. It's not the definition. Like maybe some experiment you get that maybe in different order. You get 4 first, and then 2, and then 6, and then 3, and then 5. But nevertheless, like of these 6 values, the average is what? It's the sum over the number of occurrences or number of experiments. In this case, the sum is 21 over 6, which is 3/5. And so here you will say the average is 3/5. And that kind of makes sense if you look at the distribution. If you have some nice numbers lying around in a single line, then the average should be what we call in the very first lecture is it was the center, the center of all of this data. If you listen more as numbers on the line 1, 2, 3, 4, 5, 6, and I ask you to find the center, you would point at this part, which is 3/5, and this is the center. This is the average from a sample from sampling. Right, so that's the intuition. So let's throw it away and see if we can just use the formula here. Right, so here, right, in this case, it means you have to first list all of the outcomes. And it's this is where the outcomes are 1, 2, 3, 4, 5, and 6. It's the sample space, and all the outcomes are 1, 2, 6. Right? So that means we're gonna have 6 terms in the sum. In the first term, when x is 1, you get 1 here, and then p of 1. And then remember that this one it is an abbreviation of p of x equals to 1. The probability that this random variable, like this die, gonna give you the value 1. And this is a abbreviation because we know it's x, so we don't have to. And then what's next? It's 2 times p of 2, because 2 is the next possible outcome in this sample space, in this experiment. Next we have 3 times p of 3, and then 4 times p of 4, and then 5 times p of 5, and then 6 times p of 6. So this is how you expand the formula, the summation formula. There are 6 possible outcomes, so there are going to be 6 terms, and each term is going to be the sum of the value and the probability of that value happening or occurring. Here, since this is what should I can say it's a fair die. Right? It's not loaded. Each of the phases are equally likely. And so for each of them is going to be 1/6. Again, back to the previous class by the definition of equally likely events. So in this case, it's 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times. Oh, let me just slow down. This is recorded anyway. Give me a moment. That's 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. And the 6th term, you just replace each of the possibility or probability by the corresponding number. And that's gonna be give you what 1 6 plus 2 6 plus 3 6 plus 4 6 plus 5 6 plus 6 6. Which guess what? This looks the same as what we have above. It's 21 over 6, which is 3.5. And so the answer here is e of x equals to 3.5. Oh, sorry, it's my head. E of x is 3.5 on average. If you roll this die, if you are looking at this random variable, then in the long run you would expect the average to be 3.5. And that's the answer. It's 3.5 sharp, right? Because we're not talking about any random. We're talking about the average in theory based on the numbers we have defined so far. But you know, maybe it's not 3.5 exactly. Like the number here is 3.5. Right? If we are talking in the probability side, right, but in statistics side, it can be any number from 1 to 6. If you are lucky and get roll 1, 1, 1, 1, 1, 2, 3, and what 4, okay, you can see there are so many low values. The sum is 12 over 6, which is 2. Then the average of that sample is 2, which is not close to 3.5. But if you repeat that enough number of times, then the average should get close to 3.5. Yeah. And so that's the basic computation of expected value, which looks like you just sum all the values and then divide it by the number of occurrences, right? Yeah, but this is when each of the outcome is equally likely. Right? The easy part. If it's not equally likely, then you have to first find p of I for each p of x for each of these x, which we did above in the same lecture, but in section 1 and 2. So that's first example. Let's take a look at the second example. Find the expected value of the sum of values of 2 dice rolls. Let's increase the dice from 1 to 2. In other words, find e of x again. And the first sentence is this is speaking language. The second sentence is the mathematical notation. Find e of x, where x is the sum of values of 2 dice rolls. Okay, let's do it. So you might want to copy the. Want to copy the formula we had before, because we did construct the table for the sum of 2 dice roll. Remember when we have a table with all 36 entries. You put the value for the first die up, put the values for the second die on the left, and for each entry you sum up these 2 values. 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, and so on. And then we count the occurrences, and that gives you what? It gives you the values from 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They have different probability now. It's 1 over 36 now, because there's only one way to get across 36 equally likely events. There's only one way to get 2. So it's 1 over 36. Next we have 2 over 36. There are 2 ways to get 3. And so on and so forth. 3 there, 4 there, 5 there, 6 there, 7 there. Oh no. It's maxed out at 7, which is the diagonal. For x you only have 5 ways left. It's 5 over 36, and then it's going all the way down to 1. So that's p of x. And just we have done this already. But now, what if we ask what is the average, the expected value? Right, so e of x is what? And just copy the formula. It's summation across all the outcomes, across all the values in the sample space, all the outcomes. And for each outcome, we take the product of that value and the probability for that value, which Right, so how many values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 values. Right, so here, down there, we're gonna get one term for each value. I think my head is in the way, but oh yeah, there it is. Okay, that's how many values are there? 12, 11. And for each value, we take a product of that value and the probability to get that value. So for 2, we only have 1 out of 36 guesses to get that, so it's 2 times 1 over 36. That's the first term plus the next term is the value times p of that value, the probability of that value. So it's 3 times what? Times the one below. And you can kind of see that the reason why we have to construct the table is that's why I suggest you construct a table this way, because it's going to be easier to compute the expected value in this fashion. So for 4, the probability is 3 over 36, and so on and so forth. 5 times that, 6 times that, and so on, all the way up to 12. For 12, we go back to, oh, it's not 12. What did I write? 26. So it's all the way to 12 times 1 over 36, and I think that's yeah, out of the range. Alright, so that's all the sum, which is, you can see that's a lot because there are so many possible outcomes. But don't worry, I'm not gonna ask you to write this many on exams or homeworks or anything. So and once you have that, then what we do next is to just sum them up. Right? If you have and I suggest in this step you use your calculator. It's gonna give you eventually 7. Now they know it's 7 because I did it beforehand before I am teaching this class. So the answer is 7. So on average, you would expect the sum to be 7. And in this end, it kind of makes sense, right? Because what value do you see the most? It's 7. You see the most. And this shape is kind of symmetric. Right? The probability to get a 6 and 8 are the same. And if you kind of take the average of 6 and 8, you're gonna get 7, the value in the middle. And so they kind of make a pair of values that sum to 17, 14 or something. But anyway, once you compute that, it's 7. And so we say e of x is 7. On average, in the long run, the expected value of this experiment, of this random variable, is 7. That's the answer. And that's the second example. Another dice. Let's take a look at something that is not dice. The value, but something. And this is not the common example that I see in textbook or something. Wait, an idea. So suppose the box contains 3 red balls and 5 green balls. It doesn't look red and green because you use different colors. But anyway, 3 red balls and 5 green balls. So now, what you have in your head is 3 red balls and 5 green balls. And then the question is find the expected number of red balls if you take 3 balls without replacement. Or in this part you have to go back to a number of lectures ago. And when we say without replacement, it means we take 3 balls out at the same time. And if you say with replacement, this would be the if it says with replacement, it say you take a ball, take a note of what color it is, and put the ball back. Replace it back to the back. Replace the ball back to the back. And so that's what I mean by replacement. But here it's without replacement, so we take 3 balls out at once. Then we count how many pink balls are there. Like first, before we compute, like can you guess what the number would be? Would you expect to see 0 pink balls? Or sorry, red balls, no balls at all? No red balls at all? Or would you expect about 1 red ball, or 2 red balls, or 3 red balls? And this is before we compute. Okay, so let's say, do you expect it to see 0 red balls? No, because we see the content of the bag that there are some red balls in there. About a half. And so the number is not going to be 0. Unless you are unlucky. And so this is not going to be close to 0. What about 3? Did you expect to take 3 balls and get all red balls? Of course not. And because there are lots of green balls. And so you're gonna expect to get some red and green. Right? Then what about 1 and 2? So we kind of see that it's between 1 and 2. You think it's close to 1? For example, 1.2, 1.3. You think it's close to 2? Like 1.9 to 2.1. And this answer is it should be close to 1. Because there are more green balls, so it should be more likely to get the green balls than the pink and the red balls. Right, so if you have 4 red balls and 4 green balls, then you can answer immediately that the average should be 1/2. Of those 3 balls should be half and half. But since there are fewer red balls, then it should be smaller than 1/2. In other words, it should be close to 1. Right? Again, without having to compute anything, if you use the correct intuition, you should get a number that's kind of like 1.2 or 1.3 or something. And then the real question is, what is that number exactly? Right, so let's compute it. So what do we have? We have to find e of x. You can kind of see I'm leaving some spaces there. Right, so again, it's you take the sum for each of the outcomes, for each of the element in the sample space. You take this product of x and p of x. What is x? The question didn't define x for us, and this is our job. But first, we have to define x. And what are we looking for? We are looking for the number of red balls. So we just let x be the number of red balls. And I'm going to be abbreviate. And you can read the whole sentence in lecture. Number of red balls from the experiment. It's not just any red balls from the experiment. And if you want to be you have to be exactly precise, you have to also copy the word the number of red balls from taking 3 balls without replacement. And this is the experiment we are talking about. That would be the experiment. But let me abbreviate it there. And then what do we first what are the possible values of x? Because it is maybe a table there. It is 0, 1, 2, or 3. 0. You could get 0 red balls, you could get 1 red ball, you get 2 red balls, and you get 3 red balls. And so these are all the possible values. And then what next is we have to find the probability for each of the outcome. And now this is where you have to stop and think. Are they all 1/4? It's not, right? It's you can always just put the numbers there. But they are not 1/4 because again the content, the number of balls are different, and that it should be less likely to get no red balls. It should be more like less likely to get all 3 red balls, and also to get no red balls at all. And so now we have to compute. What kind of tool we have? What kind of tool can we use to compute this? The answer is we're gonna have to go back and use the counting principles. And this is where it's getting more interesting. So let's say how many ways can we? First of all, how many ways? And total number of ways. Total number of ways. Or in this case, it is a combination, right? Because we take all at once and we don't care about the other. We just want the balls. So in this case, we are dealing with combinations. And what are the total number of combinations are there? There are 8 balls. We take 3 balls. That means it's 8 choose 3. Each ball you choose 3 balls. And if you compute it correctly, you should get 56. And there are 36 ways, 56 different combinations Oh, and assuming that each of these balls are, let's say they are level. Like whenever you count, sometimes it is easier to take the labels on there. Like, let's say they are all different. Like, so there are 8 different balls, and the number of combinations is 36. So how many ways you can get 0 red balls? How many combinations are there that contain no red balls at all? Okay, so to get no red balls, you have to get all green. And to get all green, it's 3 green. Put the red balls. You should get 3 greens. Right, and that means what are we doing now? We just have to use some kind of combination. To get 2 green, you have to take one of these 3. You have to take 3 greens from one of these 5 green balls. And you have to choose 3 green balls out of these 5 green balls. That means the number of ways is 5 choose 3. And there are 5 green balls, take 3, which can be what, like, can be like these 3 green balls, or these 3 green balls, or these 3 green balls, and so on. And there are lots of combinations, and the number here is exactly 5 choose 3. And just up over the time. 5 choose 3, which is what? 10. There are 10 ways to. There are 10 combinations that contain no red balls. And since there are 10 combinations that contain no red balls, and there are 56 combinations in total, that means the probability of getting no red balls, the probability that random variable is 0, is exactly 10 over 56. And here we can use the very first definition of probability, and because we treat each of these outcomes as separate. Out of 56 different combinations, 10 of them are the combinations we are looking for. So it's 10 over 56, and that means this is now we get the first number is 10 over 56 there. 10 over 56 is about like 1/5, which is still kind of fine. Right, now we finished that. Next, how many ways we can get one red ball. That means we're gonna have to get 2 green balls. Right. So how many ways are there? Do you remember what we should do here? And here you can see there are 2 different processes. First, you have to get the red ball, get the single red ball, and then you get 2 green balls. That means we can use what? The rule of product. We are describing 2 different processes. Take arrangements and take a red ball. And how many ways you can take the red ball? A single red ball. The answer is 3. There are 3 ways to take one red ball, because there are 3 red balls to choose from. And then how many ways you can take 2 green balls? And there are 5 to choose from, and you have to choose 2. So it's the 5-2. Right? And you also have to ask, do we have to divide it by 2 or switch the order? And the answer is no, because it doesn't matter if you take green or red first. You're gonna get them all out of the bag anyway. And so here by the Europe product, these 2 are, and these 2 are separate events. They are independent. And so it's 3 times what? 5 choose 2 is 10. So the number of where is 10 times 3, which is 30. There are 30 combinations that result in 1 red ball and 2 green balls. And so the probability of getting exactly 1 red ball, which is over my head, is again 30 over 56. Out of 56 combinations, 30 of them have 1 red ball. So that's the second number. Like we do 30 there. Next, you can do it in your head. Like if you get the idea. If you want 2 red balls and 1 green ball, to get 2 red balls, you have to pick 2 Okay, it's a raw product because these two are independent. Okay, first we take two red balls, which is 3 choose 2. Yeah, 3 red balls, we have to choose 2. So it's 3 choose 2. And then we can take the green ball, which there are 5 ways. Or 5 choose 1 if you want to, but that's same as 5. Okay, so that's 3 times 5 is 15. So the probability of getting exactly 2 red balls is 15 over 36. And we get the third number there. This is 15 over 36. Well, by the way, there is no formula for this kind of experiments. You have to do it one by one. There are formulas for similar kind of experiments, but for combination you have to use it. And finally, to get 3 red balls, that means to get no green balls at all, so we can just ignore it. And how many ways you can take 3 red balls? There's only one way because there are 3 red balls. You are forced to take all 3 red balls. So the probability that you get all red balls is 1 over 36. Oh, sorry, it's 56. My bad, 56. And that's the last number, like 1 over 56. And this is not required, but it is recommended. If you should sum them up and see if you actually cover all the cases. So if you have cover all the cases, then the sum should be 1. And the sum is 10 plus 30 plus 15. So it's 40, 55, 56. So that means you have covered all the cases, all the possible cases. Right, so the sum is 1, so we are happy. Right, so that's the first part. And the first part is not about expected value, or it's about constructing this kind of table. And once we have the table, now we can compute the expected value. So there are 4 different outcomes. We're gonna have 4 terms, and each term we're gonna have to multiply the value by the probability. The first one is gonna be 0 times 10 over 56, which you need to put it there to make sure you get all the cases. Next we have 1 times 30 over 36. Next we have 2 times 15 over 36. And lastly we have 3 times 1 over 56. And that can do the math. That's 0 times 10, 1 times 30, 2 times 15, 3 times 3. Everything over 36. So it's what, 66 over 56. And that's the answer. 56 over 56. And if you do the math, if you write to the decimal, it can be 1.18 or something. Oh, which is, see what? It's close to what we just discussed. Okay, so it should be 1 each. 1.2 in this case, and the exact number is 66 over 56. Which means we did a good job of approximating that value. And so that's how you compute the expected value. And that in this case you have to split them into 2 problems. First, get the table of all the outcomes and probability for each outcome. And then you use that table to those values in that table to compute the expected value. Alright, that's 35 minutes. Alright, that's a thing. That's, yeah. So because we pass for some properties of expected value